Hi, my dear GATE students. Welcome to VEDA GATE Academy. Now we can able to discuss EDC, electronic devices and circuits, right? So electronic devices and circuits, shortly you can call as a EDC. So which is one of the more weightage paper in a GATE exam. So which can almost cover 12 to 13 marks in the GATE exam. And not only in for GATE exam. So this EDC part is very useful for all other competitive exams, right? ISRO, DRDO. So any research side if you go, so this EDC part is nothing but mainly useful. And this EDC part makes that electronic devices to be very compact, So by that nowadays that electronic circuits commonly called as a micro electronic devices user. So that is the advanced development technology from EDC part that as VLSI, right? So this EDC part can also be useful to you in the analog circuits. So analog circuits would be the continuation of this EDC part. So both EDC and analog circuits in the GATE exam, you may score an average, how many means around 18 to 20 marks you can call. So that both EDC and analog circuits carries good marks for ECE students. So now you can able to check out so what this EDC contains for the GATE exam. So see this one of the syllabus contents for the EDC part. So first of that one, carrier transport phenomenon in silicon. Carrier transport phenomenon in silicon, you say. So this one is the first chapter, carrier transport phenomenon in silicon. Next one is what you can call means diodes. Next one is BJT. Next is FET and MOSFET. Right. Other than that, so VLSI part you can call. So this comes under EDC part. Okay, carrier transport phenomenon in silicon. Next one is a diodes part, BJT, FET and MOSFET you can call. Other one is nothing but what means VLSI. VLSI stands for very large scale integrated system, So in this diodes part, again you see this one now, you can able to learn PN junction, basic PN junction theory part. So basic PN junction theory part you can discuss. Other than that, you can also discuss about special diodes. So you can also examine some special diodes here. That is LED, okay, light emitting diodes, photodiode, solar cell. So these are also be included in this diodes part you can call. Let us see this one now. What is the weightage of the marks in each paper you can able to, in each subject, in each chapter now you can able to check out. So first one of that one is nothing but a carrier transport phenomenon in silicon. So what is the weightage of this one means it can score around 2 to 3 marks. Understood now? So the carrier transport phenomenon in silicon can score around how many marks means some 2 to 3 marks you can call. Okay. So next one diodes. In this diodes, the basic PN junction theory part can able to carry around 1 to 2 marks. This can score around 1 to 2 marks user. And special diodes is there. That is nothing but again, I told you LED, photodiode and solar cell. So those are the optoelectronic devices you say. So that can also score around 1 to 2 marks. Right. Next one is nothing but BJT, bipolar junction transistor you can call. So in this BJT, so you can able to get around 1 to 2 marks. Right. So FET stands for field effect transistor, MOSFET stands for metal oxide semiconductor field effect transistor. So in the GATE syllabus, originally FET syllabus not there. So originally have only MOSFET, that is a depletion MOSFET and enhancement MOSFET you can call. So why commonly can able to discuss first FET, after that only can able to go for MOSFET. So FET concepts are very useful whenever you can go into discuss what means MOSFET. So, but in the GATE exam only MOSFET is there. So commonly you are able to discuss first FET, after that only can go for MOSFET. So what is the necessity to discuss FET means the FET concepts are very useful in the other competitive exam also. So by having an idea about FET, it is easy to go through the MOSFET. Okay. So this can able to score around 2 to 3 marks. Okay. So next one is nothing but VLSI, very large scale integrated technology you can call. So in this one, we can able to discuss that application of MOSFET that is called as a CMOS technology. So that is nothing but logic designs using CMOS and NMOS you can call, and as well as CMOS transfer characteristics. So all the stuff, that type of things we may discuss in this VLSI part. So this can able to score around 1 to 2 marks. So these are the weightages of the marks for this corresponding EDC part. So carrier transport phenomenon in silicon that can able to score around 2 to 3 marks I call. Diodes PN junction theory part that can able to score around 1 to 2 marks. Special diodes again carry 1 to 2 marks I say. Right, BJT bipolar junction transistor. So here just we can able to discuss the characteristics of a BJT and what are the other things of the BJT can discuss. The continuation of the BJT mainly comes in analog circuits. Right. So that can able to score 1 to 2 marks. FET and MOSFET I told you. So among this only MOSFET is there for GATE exam. So FET is not there, but FET concepts you can discuss because it is very useful for the other competitive exams you say that can score 2 to 3 marks. So VLSI very large scale integrated, that should be the applications from MOSFET, right? So that can able to score how many marks? 1 to 2 marks. So this EDC part again may consider in the analog circuits because here all electronic devices you may learn in this EDC part. So the application of these electronic devices, suppose that diode applications. What is the diode applications? Rectifiers, right? Clipping and clamping circuits, regulators, right? Zener diode is a regulator, So this type of applications of diodes may come under analog circuits. BJT applications, BJT used as an amplifier. So BJT amplifiers, MOSFET amplifiers you can discuss. Not only that, feedback concepts. So in the case of an amplifier already whenever you can amplify the signals, right, some distortion to be present at output. So how to make that distortion to be less at output means by the introduction of feedback concepts. So that type of feedback concepts you can discuss in the analog circuits. And as well as BJT application or MOSFET application, right, that can be considered as an oscillator, right. Other than that, integrated chip based device of oscillator that op amp. So this type of things you may going to discuss in the case of analog circuits. So analog circuits will be the applications of these electronic devices you say. So both EDC and analog circuits can carry around what I told means 18 to 20 marks. I think that in the GATE exam, the qualifying marks for EC students is nothing but around what means 24 to 25 marks almost. So that most of the marks you can easy to score from both EDC and analog circuits, right? So now you can able to check out what are the reference books that can be considered for this EDC part. So these are the reference books commonly you can able to prefer that it can be common for both EDC and analog circuits. So one of the reference book I can say that what means microelectronics, okay, by Sedra and Smith. This is one of the book you can call, right? And one more reference book you can also go, that is what means microelectronics, okay, by Donald A. Neiman. So this is one more book you can call. So Microelectronics by Sadra and Smith, one of the reference book. Other reference book is another by Donald and A. Neiman I can call. So these are the reference books which are common for both EDC and analog circuits. So if it come back to this EDC syllabus, you see this one now. In the first chapter, carrier transport phenomenon in silicon, there you learn fundamentals. So the first chapter is nothing but the base for the remaining part of the EDC part. And once again, it is most useful in the analog circuits. So what is the base means here? In the carrier transport phenomenon in silicon, that is nothing but commonly that semiconductor physics you can call. In this chapter, you can able to learn about atomic structure, energy band diagram, and based on the energy band diagram, you can able to examine what is a conductor, what is an insulator, what is a semiconductor. So you can able to classify these conducting materials like conductor, semiconductor, as well as non-conducting body of insulator with the help of energy band diagram. After that, now you can able to identify the types of semiconductors. So that is nothing but intrinsic and extrinsic semiconductors, and what are the current carriers in this semiconductor like electrons and holes, and what is the current mechanisms. So what are the properties of these semiconductors? All these type of applications, all these type of things you may going to learn in this first chapter of carrier transport phenomenon in silicon. So this is the base for EDC part. So if the student well known about this, then it is easy to go through what means remaining part. Right, in the diodes part, you can able to examine what means whenever you can combine p-type and n-type material together, what happen. So the resultant formation you can call as a diode. So what are the diode, what are the working condition, what are the characteristics, and what are the type of special diodes, Zener diode, right, varactor diode, Schottky diode. So next to optoelectron devices like LED, photodiode, solar cell. So everything is a diode, but why do you call that with the different names and with the different characteristics and different applications means? You know that in the case of semiconductors, the main important thing is nothing but doping. So doping is a very important concept in the case of semiconductors. So using this doping phenomenon, the semiconductor characteristics are changing, and as well as their applications also get different, you can call. So that type of things you may learn in the diodes part. And you know that BJT, bipolar junction transistor, it was the first semiconductor device that can be used as an amplifier. So before this BJT, you know that that is in the first generation computers, the corresponding amplifier circuit made by what means vacuum tubes. Vacuum tubes are large in size, expensive, consuming more power. All these are the practical drawbacks of vacuum tubes. Once the BJT developed, the use of that vacuum tube should be replaced. So by whom means one of the semiconductor body that to be that BJT, right? After that, what sir means one more semiconductor body that can also act as an amplifier like BJT is what means MOSFET as well as FET. So these are also the semiconductor devices like a BJT that can also be used as an amplifier and switching devices. And this MOSFET is very popular nowadays in VLSI designs, very large scale integrated. So one by one concepts you can able to discuss in this. So if you are very thorough with these chapters, then it is easy to go through the applications of this EDC part that it comes in analog circuits. So my dear students, so now I can able to start what means the first chapter, that is carrier transport phenomenon in silicon. I think that you are well familiar with this syllabus content. Now I can able to start what means the carrier transport phenomenon in silicon. The first chapter now I can able to go, that's simply called what means a semiconductor physics. Check out that. The first one of that one I can able to go. Carrier transport phenomenon in silicon. So simply you may call this one as a semiconductor physics, right? Now let us see this one now. In this one now, first you start with what means atomic structure. I think that you know these things in the school standard, right? But these things are very useful now. So first you can able to start with atomic structure. After that atomic structure, now I can able to go for energy band diagrams. And then based on the energy band diagram, I can able to classify what is a conductor, insulator and semiconductor, all this. Okay. So first now I can able to start with what means atomic structure I can call. Okay. You know that every particle made up of small elements. Every particle can be made up of small elements. That small elements called as a molecule, And every molecule containing again small things. That small things called atoms. And so now, so every particle made up of small elements. That small elements called molecules. And each molecule containing the small things that will be called as the atoms. And remember again, an atom is composed of three fundamental particles, right? Understood now, students? So every atom containing 3 fundamental particles. What are those 3 fundamental particles? You know, those are electrons, protons and neutrons. So every particle made up of small elements I told, that small elements called molecule I say, and so now, and each molecule containing the small things, that small things to be named as atoms. And each atom is composed of 3 fundamental particles I said. Those 3 fundamental particles, you know, electrons, protons and neutrons. Okay, who are those? Electrons, protons and neutrons. So check up what these electrons, protons and neutrons. So now I indicate those things. So 3 fundamental particles I told to you, and so now those are what I say here, carrier. Okay, so what is the charge of them, right? And so now, and whatever the polarity, okay, polarity of charge, and whatever the mass of the carrier I go, and what is the property of that. Okay, now I can able to consider carrier, charge, polarity, mass and property. So what are the carriers I told to you? Those are, first one of that, electron, right? So what is the electron charge means, you know, 1.6 into 10 power minus 19 coulombs. Electron charge is how much? 1.6 into 10 power minus 19 coulombs you can call. One more is what you say, proton, right? So proton also have the same charge like an electron. That also how much means 1.6 into 10 power minus 19 coulombs. So both electrons and protons have the same charge, right? And whatever the neutron, you know, third one. Okay, next one of that I go, neutron. Neutron is a neutral particle, means no charge. Neutron is what means a neutral one that do not have any charge. So both protons and electrons have the same charge, but neutron, what I said, neutral. Neutral means no charge on that. And now come back, what is the polarity of this one now I say? So whatever the polarity of this one now, electron is a negative charged particle. The polarity of this charge is negative for electron. The polarity of the charge for proton is nothing but what means positive. So proton is a positive charged particle. Electron should be what? Negative charged particle you can call. And neutron is a neutral particle that has no polarity again. Okay, so electron should be a negative charged particle. Proton is a positive charged particle. Neutron is a neutral one that do not have any polarity. Okay, and again I go back, mass. What is this mass of this each carrier I go? So if I go for mass of electron, that you know is standard value 9.1 into 10 power minus 31 kg. So mass of the electron is how much means 9.1 into 10 power minus 31 kg. That should be the mass of electron you can call. And if I go for proton, so proton is a heavy particle in the given atom and whose mass is approximately how many times means nearly around 1840 times to electron you can call. And so now, so the mass of proton is 1840 times to electron. 1840 times to electron you say. So as compared to electron, right, proton mass is heavy, that is around 1840 times you say, right? And so now, not only proton, neutron also almost have the same mass. So you remember that in the given atom, who are the heavy particles means those are protons and neutrons. So protons and neutrons are heavy particles and whose mass is around 1840 times to that of electron you can call. Such that I think that you know in the school standard you learn that atomic mass or atomic weight can be mainly expressed by calculating number of protons and neutrons in a given atom, right? So understood now the students? So commonly you know that in the school standard atomic mass or atomic weight that to be calculated by counting the number of protons and neutrons in a given atom. As compared to protons and neutrons, electron mass is negligible. right? So who are heavy particles means proton and neutron are heavy particles you say, right? Atomic mass or atomic weight is mainly expressed by number of protons and number of neutrons in a given atom, okay? So what are the property indicated? See, so now among these three carriers, who can have a mobility? That should be only electron. Electrons have a mobility and they can able to move in a given crystal lattice. So they can be movable. So electrons can be movable, you can call. So due to its mobility, they can able to participate in the conductivity. So electrons are the mobile carriers you can call. They have a ability to travel in a given crystal lattice you say. So based on that, they can able to participate in the current conductivity, right? So what are that proton? So proton have the same charge like electron, but the thing is, Adipad, you remember now here, proton is a stationary, right? Proton should be a stationary particle. Stationary means fixed in position. It is unable to move, you can call. So it is unable to travel. It is fixed in position. Okay. So even it have the charge like an electron, because it is fixed in position such that it is unable to participate in the conductivity. So you don't expect the conductivity by the proton. What sir means? The proton is a stationary person, fixed in position, unable to move, so that even it have the charge like an electron, it do not cause the conductivity. Got it? Okay. So not only proton, neutron also the same thing. Not only proton, neutron also same you can call. So neutron is also stationary you say. So who are the stationary persons in the case of atom means? Those are proton and neutron. So even the proton have the charge like an electron, because of its fixed position, it is unable to participate in conductivity you say. What about the neutron means? A neutron is a neutral particle, so it is also stationary, I told. So this is the carriers who considered inside the atom, and how they can be placed in the atom, that you can able to examine now. And if you go for normal atom, in any normal atom you say the number of electrons and protons are equal. I think that you know, in any normal atom, the number of electrons and protons are equal, you can call. So how do you know this one means? That to be known by atomic number. Understand now? So in a given normal atom, electrons and protons are same in number. That to be known by atomic number, you can call, my dear students. Okay. What is that atomic number means? That atomic number indicate how many electrons and or how many protons in a given atom. That to be called as an atomic number. Suppose commonly you know that the type of semiconductors you may use is germanium and silicon. So what is the atomic number for germanium means? Say this one now. So atomic number express what I say? The number of electrons or number of protons in a given atom I say. So this atomic number is how much means? This is 14 for silicon. Suppose if go, atomic number is 14 for silicon. 14 means 14 electrons and 14 protons are there. Suppose if I go for one more semiconductor, that is nothing but germanium, you can call, how much it is means? 32 for germanium. So it have 32 electrons and 32 protons you say. Understand now? So atomic number express how many electrons or how many protons in a given atom. In any normal atom, number of electrons and number of protons would be same. That to be known by the atomic number I told, and that atomic number is how much means? 14 for silicon and 32 for germanium I told. Remember this? So now let us see this one now. How they can be placed in the atom. I indicated three particles, electrons, protons and neutrons. Now I need to know how they can be placed in the given atom. That I showed you now. So see this one of the atomic structure now. So the corresponding carriers should be placed in the given atom like this. See this one now. The protons and neutrons are located at the center part of an atom. Protons and neutrons are located at the center part of an atom. That center part of an atom called as what means? Nucleus. Got it now? Right? The protons and neutrons are located at the center part of an atom. That center part of an atom called as a nucleus. So anyhow, you know that neutron has no charge, right? Remember that? Neutron has no charge, but protons are positive charged persons. So on a whole, the nucleus would be a positive charge carrier. Nucleus would be what means? Positive charged person. So Nucleus must be what means positive charged. Okay, and it should be the center part of an atom. Nucleus must be what means the center part of an atom, you can call. Nucleus must be what means the center part of an atom. It is a stationary. Already I told that protons and neutrons are stationary. They are fixed in position. So that nucleus must be in the stationary condition. It should be a center core of an atom. That should be stationary. That should be fixed in position, you say, right? What about the electrons? Electrons are not within the nucleus. Understand, students? Electrons are not within the nucleus. Where the electrons are there? You know that electrons must be rotating, spinning around the nucleus. Understand, my students? Electrons are revolving, spinning around the nucleus, considered by the Bohr atomic model. So according to the Bohr atomic model, these electrons can able to spin around the nucleus in either circular or elliptical orbits, you know. So these electrons are can able to move around the nucleus in elliptical or circular orbits, you say. That can be studied by Bohr atomic model, right? So this is the spinning of electrons around the nucleus, I say like this. They can move around the nucleus like this. They can be spin around the nucleus, right? And so now, so this is the electron orbits, you can call. This is the nucleus. Nucleus is a positive charged one, and this electron orbit is what means negative charged one, you can call. So the electrons are spinning around the nucleus in circular or elliptical orbits, I saw, right? This one. So remember now here, all electrons are not spinning in the single level, right? They can able to spin around the nucleus at different levels, you see now. So all electrons are not spinning in a single level. They are spinning around the nucleus at different levels. Why they can spin around the nucleus at different levels? Because of their random energies. All electrons not have the same energy. Some electrons have high energy, some electrons have moderate energy, some electrons have very poor energy, you can call. So depending on their energy conditions, these corresponding energy levels I taken. Look like our human beings, you know that rich person is there, right? Middle class person is there, poor person is there. So based on that, here also electrons have random energies, you can call, such that they can take random energy levels from the nucleus. Confirm now? And again you observe now this. So this is the electron orbits of negative charged one. This is the nucleus of a positive charged one, right? So according to the Coulomb's law, so between opposite charges, which is there? Attraction is there. Who is there? Attraction. How much is the force of attraction on the electron orbit with the nucleus? How do you know, sir? Means that to be known by the term that to be called as a binding energy. That to be called what? Binding energy. So remember now, here binding energy is not the meaning of energy of the carrier. It is a measure of force of attraction between the electron orbit and the nucleus. Confirm my option. Binding energy is not the meaning of energy, you say. It is a measure of force of attraction between electron orbit and nucleus. See this one now, what I say? One of the term I introduced, students. What is binding energy? What is this binding energy now, I say? It is a measure of force of attraction. It is a measure of force of attraction between electron orbit and nucleus, you can call. Measure of force of attraction between electron orbit and nucleus. That to be called as a binding energy, you say. So it is a measure of force of attraction between electron orbit and the nucleus. That to be called as a binding energy. See this one now. This is an electron orbit which is very close to the nucleus. So binding energy is more. Such electron is tightly bound. As compared to the first one, the second one have less attraction because it is somewhat away. So that binding energy is less. Even as compared to the second one, third one still have less attraction because it is quite somewhat away from the nucleus. So as the distance between the electron orbit and nucleus increases, the attraction is less, binding energy is less. Suppose if the distance between the electron orbit and nucleus is less, attraction is more, binding energy is more. So who is very tightly bound means the electron of first orbit is very tightly bound. Which electron is loosely bound means the electron of last orbit is quite loosely bound because it is quite away from the nucleus. So it is a tightly bounded electron orbit. It is a loosely bounded electron orbit, you can call. Sir, who is this? Who is this? So, this is an electron of lower energy. Remember my option? This is an electron of lower energy. So, an electron of lower energy is revolving or spinning around the nucleus very close to it. Such electron is very tightly bound. So, tightly bound means more force of attraction on such electron orbit. And in order to make such electron to become free from the nucleus, I need to apply more energy on it. As compared to the first one, the attraction is somewhat less. So, as compared to the first one, the required energy to make it electron free becomes less. Again, as compared to this one, the required energy again be less. Again, it to be less. Who is this one means? This is a electron of higher energy. Confirm my option? Electron of higher energy, you say. Right? And now the students. So, as the energy of the electron increasing, it is somewhat spinning away from the nucleus. And such electron require only less energy to become free. And if the electron is revolving very close to the nucleus, such electron require more energy to become free. It simply look at what means. You know that example, some cinema theater is there. This is a cinema theater, right? So if you go for cinema theater, there you know that different blocks are there. You find out different blocks. Suppose this is a screen, right? So very close to the screen, who can able to sit means the persons who belongs to what sir means fourth class persons can able to sit, right? This is a suppose I can call some third class, second class. This is a first class of balcony. This is a cinema theater. This is the screen. So now let us see this one now. So different people may be going to be sit in different blocks we can call. So I think that you know this is a what means a costly one. Suppose I assume that this one this block containing each seat should be 100 rupees. Suppose this is around 60 rupees you can call. This should be in this one 20 rupees you say. So who can able to place himself in the third class means that is not but very poor persons. So next, if you go for this one means first class persons means somewhat rich persons you can call. They can able to purchase the ticket of each one is not but 100 rupees. So why I say all these things means see this one now. Whenever that on that screen the cinema is going to be movie is going to be running, what you can able to see that one means the heating effect concept on the screen. So which person is not but greatly affected by the heating effect of the screen means third class person. As compared to the third class person, the second class person on him the heating effect is less. Again, if you go for first class person, the heating effect is quite negligible. Is almost free from the heating effect of the screen. Same story here also. Whatever electron who is revolving very close to the nucleus, that is of a lower energy electron, such electron is tightly bound with the nucleus. And such electron require more energy to become free. And what is the electron of higher energy is away from the nucleus you can call. And such electron require very less energy to become free. When electron become free means when the electron can able to skip away from these binding levels. At that time that electron become free and such electron can participate in the current conductivity. So this is the case. So all electrons do not have the same energy in a given atom. They have random values of energy. Based on that I say that they can spin around the nucleus at different levels. So all these are called as energy levels you can call, and these energy levels are simply called as cells. That energy levels are simply called as what sir? Cells you can call. So what the name of this cells means? So the cells are named as K, L, M and N. There are 4 cells are there. So these energy levels are called as the cells you can call, and there are primarily main 4 cells are there. Those are K, L, M and N, which are always be directed outward from the nucleus. Come to my option. These cells are directed outward from the nucleus. How many cells are there? 4 cells are there. What are those? K, L, M and N. And so now, so what that way means that always be directed outward from the nucleus. So these are the primary cells you can call. And so now let us see this one now. If you consider that cinema theater, in each section, the number of seats are limited, right? First class, second class, third class. What are that occupancy of the seats should be not be unlimited, sir. It should be limited number. Like that, the same story again here, students. How many electrons are allowed in every cell? That is not be unlimited condition, that must be limited. So every cell, the number of electrons that can be considered to be occupied should be limited number, not be any number you can call. Confirm my option. So these energy levels I can call as a cell I told, and what the occupancy of the electrons in every cell means, that should be limited I told. How do you know that number means? That number I can able to examine by a term that to be called as a principal quantum number. That number is called what, sir? Principal quantum number. What is this principal quantum number? That you can able to examine. Okay. So in any cell, the number of electrons must be limited you can call, and that number you know with the help of the term that to be called as a principal quantum number. So what is that principal quantum number I can able to examine? See this one now. So the number of electrons in any cell should be limited I told, that to be known by a term that is called principal quantum number I say. Confirm my option. So that number is what you can call, sir, principal quantum number. What is this principal quantum number means? That principal quantum number expressed by the term that is what you can call 2n square. Principal quantum number to be indicated by what? 2n square. That is a small n there, not capital N. This small n indicate what means? Integer. Got it now? So principal quantum number can indicate how many electrons are considered in each cell I said. So that to be known as a 2n square, where n stands for integer you can call. Let us see this one now. What are the cells I told to you? The cells I told to be like this. These are the cells. Who are those? K, L, M, N. So which are always be directed outward from the nucleus I told. Now I can able to examine that. So this is the thing I say. Cell. Okay. N. And other one is what I told. Maximum electrons allowed. Maximum electrons allowed I say. That to be expressed by principal quantum number. That I told you 2n square. Okay. Now indicate those for corresponding 4 cells I said. Those are K, L, M, N. Understand now? Understand also, students? So what are those cells? K, L, M, N you can call. What is that value of N for this? 1. This is a 2. This is a 3. This would be 4. Understand now? For K cell, N is 1. For L cell, N is a 2. For M cell, N is a 3. For N cell, N is 4. This is small n. This is capital N. Observe now the difference. So now I can apply this one. Maximum electrons allowed by defined by principal quantum number. So that I told as a 2n square. Now I can able to go for it. 2 into 1 square. That is a 2. Right? 2 into 1 square means a 2 only. Next I can go for this. 2 into 2 square. 2 4s are 8. Next 2 into 3 square. 3 square means 9. 9 2s are 18. 2 into 4 square. That is nothing but what you can call 14 square. 2 into 4 square. 4 square means 16. 16 2s are 32. So these are to be the maximum electrons allowed in the corresponding cells. For K cell, maximum number is a 2. For L cell, it is 8. For M cell, it is 18. For N cell, it is what? 32 we can call. Check up now. What are the thing of that? So for K cell, how many I told? 2. For L cell, I told 8. Here it is 18. Here it is 32. Got it now? 2, 8, 18, 32. Right? So in any cell, the number of electrons allowed must be limited. That to be known by principal quantum number. So principal quantum number to be expressed by 2n square. Based on that, for K cell, maximum electrons allowed is 2. For L cell, it is 8. For M cell, it is 18. For N cell, it is 32 I told. And so now? Okay. So how the electrons occupancy is considered? Remember now, occupancy of the electrons in an atom must be start always from K cell. Once K cell is complete, then only can go for L, then only can go for M, then only can go for N. This is the way of occupancy of electrons. So once K cell is completely finished, then you can able to start L, next to M, next to N you can call. And one more thing, students, remember now, for a given atom, any cell may consider as an outermost. Don't say n to be the outermost for all. Alright? So, depending on the electronic configuration, any cell may consider as an outermost for a given atom. So, don't say compulsory the n should be the outermost for all. Right? So, any cell may consider as an outermost, right, for a given atom, you can call. So, is it right or not? Now, I can able to show to you. Suppose, you know that silicon atomic number, how much you know, sir? That should be 14, you know. Silicon atomic number, how much you know? 14. That is 14 electrons are there. Now I can able to go for silicon. This is a silicon atom that have 14 electrons. How these 14 electrons are occupied in the corresponding atom, you can able to go for. So K cell, 2 electrons, filled 1. So among 14, 2 are over. Next, L cell, 8 over. 2, 8, 10. Then how many left out? 4 are left out. Come back to M cell. M cell originally want how many? 18. But how many left here? Only 4. This one over. 2, 8, 4. So for silicon atom, according to the atomic structure, who should be the outermost means M cell should be the outermost. Why don't you say N means? Because I say that M not complete here. Without completion of M cell, how can I express N cell? You can call. So, who to be the outermost for a silicon atom means that to be M only, not N. Suppose if I go for germanium, you know that germanium atomic number what sir means 32, you know. So, atomic number for germanium is nothing but what you know, 32. That I can able to check out. Suppose I can consider for germanium. Germanium atomic number, you know, 32. Atomic number of germanium is what you know, 32. Now I can able to place this one. First one, 2. Over. Next, 8 over. Correct? 2 plus 8, 10 over. Next one, what is? 18 is there. Over. So, 2 plus 8, 10 plus 28 plus 18 means 28. So, this is for germanium. 2, 8, 18. 28 over. Then, how many left out? 4 are left out. That should be here. So, who should be the outermost for germanium means? That is nothing but a N. That's my option. So, depending on the electronic configuration, what I say means any cell should be the outermost. Don't say compulsory the N should be the outermost. That may be M or N, whatever it may be. Any cell may consider as an outermost. Why do you say all these things means? Now, I wanted to introduce one of the term. So, when do you say that atom is a stable or unstable? So, how do you know the atom to be stable or not? That to be expressed by means of this distribution of electrons. Remember now, according to the Bohr atomic model, you say that an atom look like be stable if its outermost cell is complete. That is the ideal statement. Understood, my student? So, an atom look like be stable if its outermost cell should be complete. Then it will be called as a stable atom. Otherwise, it is unstable. An atom look like be stable atom if its outermost cell, whatever it may be, I don't call, that is completely filled, then it should be stable. Otherwise, it is unstable, you can call. Suppose if I go for silicon, who should be the outermost here? M. In that M cell, how many are there? Only 4 are there. But original I require how many? 18. Not complete. So, it's not stable. It's unstable. Right? Germanium here, 32 are there. So, occupancy of the electrons is like this. Whose outermost is nothing but N. In the N cell itself, originally I need 32. But how many are occupied? Just only 4. So, it's also not complete. It is also unstable. Confirm now? So, an atom look like be stable. Right? If its outermost cell is complete, then it look like be stable only. Otherwise, it should be unstable. Okay? And Bohr proposed a new model of stability. So, he said that an atom may also look like be stable even its outermost cell is not complete. Confirm my option? Original ideal statement is what I told. So, an atom look like be stable if its outermost cell is complete, I told. Right? But I say now what? Even the outermost cell is not complete. Right? The atom look like be stable, I say. How do you say this one means? That to be considered by the Bohr modified principle. So, according to the Bohr modified principle, what I say means an atom look like be stable even the outermost cell is incomplete, right? By having a minimum of 8 electrons in the outermost. Confirm my option. Even the outermost cell is incomplete, the atom look like it be stable if it have a minimum of 8 electrons in the outermost. If it have a minimum of how many electrons? 8 electrons. So here outermost only 4, not be stable. Here also 4, not be stable. So originally, if the outermost cell is complete, it is a stable. Or even the outermost cell is not complete, it look like a stable by having a minimum of 8 electrons, right, in the outermost. So this is the outermost for silicon. So not have a minimum of 8. This is the outermost for, so this is the outermost for silicon, right? It's not complete, so it's not have a minimum of 8. So it's not stable. This is the condition of germanium. This is the outermost for germanium. So it's not complete, and as well as it do not have minimum of 8 electrons. So it is not being stable, you can call. So how do you keep the atom as a stable? How do you keep the atom as a stable? Remember now, an atom may become stable with the help of bonding. An atom may become stable with the help of what, sir? Bonding. What is the bonding? Bonding is the force of attraction or repulsion between two or more neighbor atoms. So it is a force of attraction or repulsion between two or more neighbor atoms, by means of which you can able to carry the electrons from one atom to another atom. Right? Bonding is a some mutual understanding between two or more neighbor atoms. By that, we can able to carry or transfer the electrons from one to the another atom. That to be called bonding. So whenever the atom is unstable, it becomes stable with the help of the bonding. With the help of what? Bonding. It is a mutual understanding between two or more neighbor atoms. So by that, they can able to share the electrons from one atom to another atom. That to be called as a bonding, I call. Right? So with the help of the bonding, an atom may become stable. Right? Remember now, there are certain atoms are there. They look like to be stable without any bonding. Confirm my option. There are certain atoms are there. They look like to be stable without any bonding. Who are such one? Means those are inert gas particles. Right? In the inert gas particles, the outermost cell is complete and they don't need any bonding to become as a stable. So in the inert gas particles, I think that in the Bohr periodic table, right, that are the fourth group elements you can call helium, neon, xenon, all these things. So these are the fourth group elements. Those are nothing but inert gas particles you can call. According to their electronic configuration, their outermost cell is complete, and such type of atoms, right, outermost cell is complete you can call, so that they are perfectly stable without any bonding. Other than these fourth group elements, all remaining atoms are unstable, in which the outermost cell is not complete you can call. Right? So what is the atom? Whenever it is unstable, it becomes stable with the help of what I told? Bonding. Bonding is a mutual understanding between two or more neighbor atoms, by which they can share or transfer the electrons from one to the another atom to become as a stable you can call. Remember my option. So if you go for fundamental particles, what are that one means? Conductors, insulators. Another one is semiconductors. Who are those? Conductors, insulators. Another one is semiconductors. So if you go for conductors, what type of bonding you prefer? I think that conductors uses metallic bond. Conductors uses what? Metallic bond. If I go for insulators, ionic bond you can use. If I go for semiconductors, covalent bond you can use. That's my option. So conductors uses metallic bond. Insulators uses ionic bond. And semiconductor uses what means? Covalent bond. Check out now. What are the thing I told? Right. So an atom become to be stable, right, by having a minimum of 8 electrons in the outermost cell, or completely filled, I told. Confirm an option. Suppose if it is unstable, you can able to improve, you can able to make it as a stable with the help of bonding. So bonding is what I told. It is a mutual understanding between two or more neighbor atoms. By that, electrons can be shared from one to the another atom to make it as a stable. Confirm my option. Next. So I said that what type of bonding you prefer means, right, conductors uses what means? Covalent bond. Insulators uses what? Sorry, conductors uses metallic bond. Insulators uses ionic bond. Semiconductors uses covalent bond, I told. Confirm my option. So yes or no? So bonding is force of attraction or force of repulsion between two or more atoms, we can call, by which what you can call electrons can be shared, transferred, right? By which electrons can be what you can call shared between the atoms, by that the atom becomes stable. Bonding is the force of attraction or repulsion between two or more neighbor atoms, you can call. So by means of which what you can call electron can be shared to make an atom to be as a stable, right? To make an atom to be stable. Got it now? Right. So what I told means what type of bonding you may use. I said that conductors uses what sir means metallic bonding. Right. Conductors uses what? Metallic bonding I call. Next, insulators uses what I told, ionic bonding. Insulators uses what I call ionic bonding. Suppose if I go for semiconductors uses what means covalent bond. Conductors uses metallic bonding. Insulators uses ionic bonding I call. Semiconductors uses what means covalent bond. By that they can able to carry the electrons or transfer the electrons from one to the other atom to make themselves as a stable one. To make themselves as what means stable one you can call. Now I can able to introduce the valence electron. Now I can able to introduce what is the valence electron. And so now, so inert gas particles I told that fourth group elements. What are that fourth group elements means in which the outermost cell is completely filled I told, and which do not ask any bonding to make as a stable. Right? Already you understand that. So next now I can able to show that one to you. What is the valence electron? So this is commonly used word here. You understand now what is the valence electron? So now I can able to express this valence electron, students. Valence electrons are those in the outermost cell of an incomplete atom. Confirm my option. And so now these are the electrons in the outermost cell of an incomplete atom. These are the electrons in the outermost cell of an incomplete atom. Those are called valence electrons. Suppose if the outermost cell is complete, the valence number is 0. And so now the students, if the outermost cell is complete, then what you can call means the valence is 0. Example, I think that you know again, inert gas particles. Their outermost cell is complete, valence number is 0. Right? Suppose if the outermost cell is incomplete, there you can able to find out non-zero valence. Non-zero valence. And so now, what is the valence electron I say? It is the number of, okay, it is the number of electrons in the outermost cell. In the outermost cell of an incomplete atom. Right? So, valence electrons are the electrons in the outermost cell of an incomplete atom you can call. Right? Suppose you to discuss that atomic structure. You discuss that atomic structure here. Says for now, germanium and silicon. Here for germanium, outermost is N, so it is incomplete one. It have the electrons of 4 in this incomplete outermost cell that are called valence electrons. How many valence electrons are there? 4 valence electrons are there. That is called tetravalent. Okay. Suppose if you go for silicon, This is the outermost cell is M, so it is also not complete one. In this outermost cell, how many electrons are there? 4 are there. So these are valence electrons. This is called the 4 valence electrons are here. That is also tetravalent. So both germanium and silicon each have 4 valence electrons in their outermost cell. Both are tetravalent. You can call both are what? Tetravalent. Understand now these things? Okay. So germanium and silicon are tetravalent. They are tetravalent one. So in which the outermost cell containing how many electrons are there means 4 electrons are there. So outermost cell is incomplete there. In that incomplete outermost cell, how many electrons are there? You can call means 4. By that they are called tetravalent. So depending on the number of valence electrons, the atoms are classified into 3. Confirming option and students. So depending on the number of valence electrons, the atoms are classified into mainly 3. Those are trivalent, tetravalent, pentavalent. Right? I can able to classify the atoms mainly based on the number of valence electrons. Those are trivalent atom, tetravalent atom, pentavalent atom. Right? Depending on the number of valence electrons, this is the main classification I call. Those are trivalent, tetravalent. Another one is pentavalent. You can call. See this one now? One of that what? Trivalent. One more I say tetravalent. Right? One more I say pentavalent I call. So my students, so depending on the number of valence electrons, I said that there are 3 classifications of atoms: trivalent, tetravalent and pentavalent. Now what is that valence number I showed to you there? So now I indicate that valence number, and based on that you can also check out some examples for that. Okay, so there are trivalent, tetravalent and pentavalent I can call. I can able to discuss that. Trivalent atom in its outermost cell of incomplete, how many electrons are there means 3. In its outermost cell of incomplete, how many electrons are there means 3 are there. If I go for tetravalent, in its outermost cell of incomplete, how many are there means 4. Okay. If I go for pentavalent, in its outermost cell of incomplete, how many electrons are there means 5. Got it now? So depending on the number of valence electrons, I can able to classify the atoms as trivalent, tetravalent, pentavalent. A trivalent atom have 3 electrons in its outermost cell of incomplete. Right? A tetravalent atom have 4 electrons in its outermost cell of incomplete. Like that pentavalent have 5 valence electrons. Got it? So what are the examples of this I go? Now I can able to go for the examples of that. So trivalent you say now, aluminum, right? Gallium, right? Indium, boron. All these are the trivalent atoms. Aluminum, gallium, indium, boron. If I go for tetravalent containing 4 valence electrons I call. So just now you discuss the most popular tetravalent of semiconductor bodies. Those are germanium, silicon. Right? Next pentavalent. Pentavalent containing how many? 5. What are those? Arsenic. Example I go. Okay. Arsenic. Antimony. Okay. Phosphorus. Okay. Bismuth like this. So arsenic, antimony, phosphorus, bismuth, all these are the pentavalent atoms. So these are the examples for trivalent, tetravalent and pentavalent. Let us see this one now. The most popular trivalent impurity in the P-type material fabrication of IC technology is what means boron. Confirm my option. among all the trivalent impurities, which one is the most popular trivalent impurity used for the fabrication of P-type material in IC technology, integrated chip technology, means boron. Sir, why do you say only boron? If I add any trivalent impurity of aluminum, gallium, indium, anything, if I add any trivalent atom to a pure semiconductor, I may get P-type. That you know in the school standard, all that. A P-type semiconductor is obtained by adding a trivalent impurity, you learn, right? But I am stressed that mostly preferred trivalent atom for P-type fabrication is boron, not all. Right, in IC technology, right, in the fabrication of P-type material, which type of impurity most popular to be used among all trivalent atoms means boron. Sir, why do you prefer boron as compared to all others? Anybody can guess here? What the answer means? Among all the trivalent atoms, the energy gap for boron is less. So what is this energy gap? That you can examine next in the energy band diagram. So simply you remember now that energy gap less I told for boron as compared to all other trivalent atoms. What is this energy gap means? How much is the energy required for that atom, right, to make the electron to become free? Energy gap is less means less energy required to keep that electron free. Energy gap is more means more energy required to make the electron to be free. So among all the trivalent atoms, you remember now boron have a less energy gap. Less energy gap indicating that even with less energy, the charge carriers are generated, electrons are generated as a free as compared to all other trivalent atoms. So that's the main reason to use the boron as a the trivalent impurity dopant in the P-type fabrication. Boron to be used as a trivalent impurity dopant in the P-type fabrication in IC technology, right? That's the case. Now again you go for pentavalent. You know that pentavalent will be used in what fabrication? You know, N-type. So N-type semiconductor is obtained by adding pentavalent impurity, you know, right? So you can add any type of this pentavalent impurity, arsenic, antimony, any of that, you may get a N-type semiconductor. So again, look like a P-type of boron in IC technology of N-type fabrication. Who is the most popular N-type material means that to be phosphorus. So who is the most popular pentavalent impurity that can be used in the N-type fabrication in IC technology means that to be what you can call phosphorus. So phosphorus is most commonly preferred to be used. Why means look like a boron among all the pentavalent impurities, the phosphorus have a small energy gap. The energy gap for phosphorus is less as compared to other pentavalent impurities we can call. So based on that, what you can call means even at a less energy, it can able to generate the carriers. So the mostly preferred pentavalent impurity in IC fabrication technology is nothing but what means of for N-type fabrication is what? Phosphorus. Understood all these things? Okay. So the popular trivalent impurity in P-type of fabrication is a boron. The popular pentavalent impurity for N-type fabrication in IC technology is what? Phosphorus. Understood now, students? So this commonly asked in what means in IC fabrication methods for 1 mark bit in the competitive exams, right? Next, come back. One more is there. Who is that? Tetravalent. So what is that tetravalent? You know, that containing the 4 valence electrons in the outermost cell, you know. The best examples you discuss based on the current conductivity, those are germanium to silicon, right? If I compare germanium to silicon, just a small thing you remember. So I take both 2 bodies. See, Suna? These are the 2 bodies. One body is made by germanium. Okay. Another body is made by silicon. One body made by germanium. Other body made by silicon. Okay. So one body I told germanium. Other body I told as a silicon. Both are of the same dimensions. Not be different in dimensions. Physical dimensions should be same. And what will I do means I apply the same energy for both. The amount of energy I applied for both is the same. Same amount of energy I given for both materials, right? One material is made by germanium, other material made by silicon I call. Both applied to the same input energy. And if I compare their conductivity, which conductivity more? I think that, you know, conductivity of germanium should be greater than conductivity of silicon. Remember now? Which body conductivity more means germanium body conductivity should be more as compared to silicon conductivity. Understood, my students? I given two materials, one material made by germanium, other material made by silicon. Right, both have the same dimensions, only material is only different, and input energy to both of that one is same. I told if I compare their conductivity, which one I should be more, I told means germanium body conductivity more than compared to silicon conductivity. Okay, but practically you prefer silicon, even its conductivity less than compared to germanium. So conductivity of germanium more than compared to silicon. But I said that silicon to be preferred, not germanium. Germanium will not be preferred than compared to silicon. Who is most popular means silicon. I think that your chapter or title name itself a carrier transport phenomenon in silicon. So even the silicon conductivity is less, the preferred body is nothing but a silicon, not a germanium. What are the reason to prefer silicon as compared to germanium? I discussed, right? So now what I told, even the conductivity of silicon, right? Even the conductivity of silicon is less. Conductivity of silicon is less than compared to germanium. So conductivity of silicon is less than compared to germanium. Which one is preferred? I told silicon devices can be preferred, right? Why do you prefer this one means? Because these are the reasons. See this one, what are the reasons it have? First one of that. So if I compare silicon and germanium, which can be available very freely and easily in the nature means silicon, right? Available. So it should be available freely in the nature. So it should be available easily than compared to germanium. That is abundant, you can call, right? So first one of that, it is a general thing, it is available very freely or easily in the nature, you can call. That's a general thing. But main important thing what means, as compared to germanium, in silicon, minority carrier effect is very less. Such that silicon body is more stable. I think that in our BZ amplifiers, all these things, right? Stabilization is mostly required for what purpose means to keep that output value independent of what this minority carrier effect you can call. That's the stabilization process that you may learn in analog circuits. So as compared to germanium, silicon in which the minority carrier effect is less and it is quite stable, you can call. So what I say, minority carrier effect is less and it is quite stable than germanium. This is one more reason. This is very important. So first one is abundant, that is available very freely or easily in the nature, I told. Next one is what means minority carrier effect is less, right, in the case of silicon body, and it is quite stable, right? And one more thing. So what is that? Silicon made device can able to operate even at high temperature. So that I discussed later experimentally also. So a silicon made body can able to use or can able to maintain its characteristics or properties even at high temperature up to 200 degrees centigrade. Whereas a germanium made body can able to maintain its characteristics or properties only up to 85 degrees centigrade. So who to be preferable to use even at high temperature means silicon. That I can prove later in the corresponding extrinsic semiconductor of N-type and P-type, that is effect of temperature on extrinsic semiconductor. There you can able to discuss that. And so now, so silicon body can maintain the characteristics even at high temperature. So among these two persons, who to be useful at high temperature means silicon. So silicon to be useful up to 200 degrees centigrade, whereas germanium to be useful up to 85 degrees centigrade. That to be called as a critical temperature usage. That I discussed later. That comes. So who to be operated at high temperature you can call silicon, right? Silicon can operate even at what means high temperature I told. So silicon can operate even at high temperature, right? A silicon made body can operate even at high temperature up to what means 200 degrees centigrade, whereas germanium body can able to operate up to 85 degrees centigrade only. So who to be preferable to use at even at high temperature means silicon. So because of all these reasons, silicon is mostly preferred than compared to germanium. That's the main reason you can call. So one is abundant, that is easily available in the nature. Other one is minority care effect should be less in a silicon made body. So it is quite stable, and as well as the main other one is nothing but it can maintain its characteristics or properties what it may be even at high temperature up to 200 degrees centigrade. Whereas germanium made body can able to maintain its characteristics up to 85 degrees centigrade only. So why this germanium body have more conductivity than compared to silicon? Even you can apply same input energy means that's only the thing is what means germanium resistivity is less than compared to silicon. The resistivity of germanium is very less than compared to silicon. Based on that, the germanium body can have more conductivity than compared to silicon. That's the main reason. No other reason for that. So germanium made body, why it can have more conductivity than compared to silicon body of same dimensions means the thing is in germanium resistivity is less than compared to silicon. So even silicon conductivity is less, but preferred one is the silicon in our IC fabrication conditions or in our semiconductor appliances. The mostly preferred material as compared to the other one is what means the silicon IC, right? So now, so who is mostly preferred? Tetravalent impurity means so that is a pure semiconductor. We can also call that to be silicon. The most popular trivalent is a boron, pentavalent is a phosphorus, and the tetravalent is a silicon. Understand these things? So valence electron you learn first. Valence electrons are the electrons in the outermost shell of an incomplete atom I told, right? So based on the number of valence electrons you discuss mainly three: trivalent, tetravalent and pentavalent. So the most popular trivalent impurity is boron, that considered in p-type fabrication. Most commonly considered pentavalent impurity means phosphorus, that can be used in the n-type fabrication I call. And tetravalent impurities are what means germanium and silicon. And if I compare germanium and silicon, the commonly preferred is silicon. Understand these things? Now, so now I can able to go for what means the atomic, based on that atomic structure. You know that atoms are classified into mainly three. Those are what means solids. Other one is what means liquid and gases. Okay, based on the atomic structure, you can again classify the atoms as three types. You can call that is another part what you can call means solid body, liquid body, and a gas particle you can call. So based on the atomic structure, these available materials are mainly classified into three types. Those are solid, liquid, and a gas particle. If you go for solid, you know that solid body is commonly called as a rigid body, in which the atoms are kept very, very close together. Confirm my option? A solid is a rigid body, in which the atoms are kept very, very close to each other, you can call. It's quite difficult to separate one atom from another atom in the case of solid. So solid have a rigidity, you can call. Rigidity means what means the atoms are kept very, very close together, and it's quite difficult to separate one atom from another atom. And solid body have good electrical and thermal properties, you say, right? If you go for liquid, in which there is a somewhat separation between the atoms, If you go for gas particles, this separation is quite long as compared to liquid. In the case of solid, the atoms are kept very close together. Quite difficult to you to separate one atom from another atom. If you go for liquid, there is a little bit separation between the atoms. And if you go for gas particles, this separation is too long. So I don't want all. So depending on my requirement, I can able to go for solid. So solid is a rigid body, you told, in which the atoms are kept very close together, you can call. So what I say? Solid is commonly called as a rigid body, right? In which the atoms are kept very close together, I call, right? And based on the atomic structure, this solid again classified into two types. What that one means? One is a crystalline solid, other one is amorphous solid, you can call. So based on the atomic structure, a solid again be classified into two types. What that one means? That is nothing but what you can call crystalline and amorphous. So one is crystalline solid, right? Other one is amorphous solid, you can call. Got it now? So a solid is a rigid body in which the atoms are kept very close together, I told, and depending on the atomic structure, a solid is further classified into two types, crystalline, other one is amorphous. What is a crystalline solid? A crystalline solid have symmetric structure. Understand now, students? What a crystalline solid means? A crystalline solid have a symmetric structure, you can call. What is a symmetric structure means? The arrangement of the atoms must be symmetric order. They not be placed in a zigzag manner like this, right? This is the atoms. All these atoms are in the symmetric manner. That to be called as a crystalline, right? This will be called as a crystalline solid. So a crystalline solid have symmetric structure, I can call. A crystalline solid have what type of structure, sir? Symmetric structure, you can call. This one have a symmetric structure. That have the symmetric crystal structure, you sir. Best example of crystalline solid is what means conductors. So best example is what sir means conductors, you can call. Conductor is a crystalline solid, you can call, right? In which the atoms are placed in a symmetric manner, you can call, not be in zigzag mode. Best example, you say this one now. NCC students in the ground. Suppose you know that NCC students are in the ground. Each and every NCC person can be placed or can be positioned in a symmetric manner with respect to the other one. They never be placed in a zigzag manner, right? All NCC persons in the ground, whenever even they can move, so every person can move in symmetric position with respect to the other. Same condition here. All atoms are arranged in a symmetric manner. That to be called as a crystalline one. So best example is called conductor, you say. Other one is what means amorphous. What is this amorphous means? An amorphous solid have unsymmetric structure. Means the atomic structure is a zigzag. So all atoms are oriented in a zigzag manner, you can call. All atoms are arranged in a zigzag manner like this. This is the this is the unsymmetric structure, you can call. All our atoms are in a zigzag manner, random manner like this. So they do not be placed in a symmetric manner. They can be placed in a random manner like this. So this is called as a zigzag structure. That to be called amorphous. So amorphous have what means? Random structure of atoms, you can call. So this is an amorphous solid. This is what you can call amorphous. Amorphous solid it is. Okay. So the atomic structure is what means a zigzag place, you say. So who is the best example for that one means? The best example for that one is what means insulators. The example of that one is what means insulators. So insulator is a amorphous body, you say. Conductor is a crystalline body. And so now students, so based on the atomic structure, you are classifying three types of materials: solids, liquids and gases. Now presently I am considering solid. Solid is a rigid body, I told, in which the atoms are kept very close together, I told. And so now, and this is further classified into two types, I can call crystalline and amorphous. What is a crystalline solid? I told a crystalline solid is one that can have a symmetric structure. That can have what I told? Symmetric structure, in which the atoms are arranged in a symmetric manner. Right. Best example for that one is conductor. Other one is what I told you, amorphous solid, in which the atoms are placed in a zigzag manner, I can call. Randomly oriented, you can call. Right. Best example for that one is insulators. Confirm my option now. So this is all about atomic structure you learn. And you discuss that in the case of atom, all electrons are not in the same energy level. All electrons are in the different energy levels, you can call, because of their random energies. So what is the probability of energy of an electron in a given atom? How do you know means? That you can able to examine with the help of energy band diagram. With the help of energy band diagram. Answer my option. So now I can able to examine the next one of that energy band diagram. What is this energy band diagram? Now I can able to show to you. So you already learn According to the atomic structure, the electrons around the nucleus have random values of energy. They don't have the same values of energy. So what is the probability of energy by an electron in a given atom known by energy band diagram? What is that energy band diagram? Now I can discuss. Energy band diagram. Now I can confirm. See, so now it looks like a progress report of a student. Suppose a student is there, right? He may learn number of subjects in its course, course you can call. But he may not score same marks in all papers, in all subjects. He can score more marks in one subject, he may score less marks in the other subject, like that. So he can able to score different marks, not same marks in all subjects. Then how do you know the performance of a student, whether he is a dull student or average student or a good or excellent student? How do you know? Means by preparing a progress report. What is that progress report? That progress report containing what subjects he written and how many marks he scored. Thereafter you find out the total and average. By that you can estimate the student performance is dull or average or good or excellent, like this you can call. Same story here also. In a given atom, all the electrons not have the same energy. They have random values of energy. So what is the range of energy or what is the probability of energy of an electron in a given atom? How do you know? Means that to be known by its progress report. That progress report for the electron or energy in a given atom, that to be called energy band diagram. So it is 100%. So look like a progress report of a student, right? For the electrons in the given atom, the energy progress condition defined by what? Means energy band diagram. So it is the probability of energy considered by an electron in a given atom, that to be called as a energy band diagram. So this energy band diagram can be partitioned into three. So this energy band diagram can be partitioned into three. What are those? Means one is valence band, other one is conduction band, both together separated by one more person, that to be called as a energy gap you can call. Now I can able to examine what is this valence band, what is that conduction band, what is that energy gap you say. And so now, so as the electrons have random energy, right, the probability of energy of an electron in a given atom known by what? Energy band diagram, right? This is that I told. The probability or range, whatever you can call, or range of energy, right, by an electron in a given atom known by what? Means energy band diagram, known by energy band diagram you can call. Understand now this, students? Right. So this energy band diagram containing how many partitions? I told 3 partitions are there. So that I can able to show that one to you. This is the energy band diagram we can call. Okay. So this energy band diagram partitioned into 3 I told. Those are valence band. Okay. One more is conduction band I call. One of that is what I said, valence band. Other one is what I can call conduction band I told. So these together separated by a gap, that is called as a forbidden gap or simply called energy gap you say. This one it is. This is the energy gap. So valence band, conduction band together separated by a gap, that is called forbidden gap or simply called energy gap you say. And according to the condition, the energy range of electron always from minus infinite to plus infinite you can call. So what is the meaning of that one? Means upper level of conduction band, lower level of valence band are undefined states. So this is plus infinite, this is minus infinite. And lowest energy of carrier in conduction band denoted by EC. So EC is a notation that indicate the lowest energy of the carrier in conduction band. EV is the notation used here that represent highest energy of the carrier in valence band. EV stands for highest energy of the carrier in valence band. EC stands for lowest energy of the carrier in conduction band. Based on that, remember now, EC equal to what means EC minus EV. EC equal to EC minus EV. And so now the energy band diagram have three partitions named as valence band, conduction band, separated by a gap called energy gap. So the energy range is probably minus infinity to plus infinity, I told, right? The lowest energy of the conduction band denoted by EC, highest energy of the valence band denoted by EV I can call. So that EC equal to EC minus EV. Let us see this one now. First one of that I go. Who is there? Valence band. What is this valence band I can call? First one of that now I can able to express valence band. What is the valence band? It is the range of energy considered by valence electrons. It is the range of energy considered by valence electrons I can call. Confirm my option. It is the range of energy considered by whom? Valence electrons. Remember now, as long as you are using the word valence electrons, that indicate that electrons are not free. Which are not free you can call. Which are not free. Got it now? So, it is the range of energy considered by valence electrons and which are not free you can call. Means, it is the range of energy considered by binded electrons which are influenced by the nucleus. So, as long as the electrons in the valence band that is completely binded with the nucleus, such electron is not be free. That to be called valence band. So, it is the range of energy considered by valence electrons we can call. As long as the word I use the valence, such electrons are not free. They are under the control of the nucleus. They are completely binded with the nucleus we can call. So, simply you may say that it is the energy range associated with the binded electrons. It is the energy range associated with the binded electrons you can call. And what the status of this valence band means? See, so now this valence band may be either completely filled or partially filled you can call. So understand my option? Valence band is either completely filled I call, either completely filled. So, or partially filled I can call. Where do you get completely filled means? That you can get in the body of insulators. Completely filled appeared in the case of insulator you can call. Or partially filled you say. Partially filled means that electrons are distributed both in valence and conduction bands. That you can get in conductors. Is it right or not? I showed there in that particles. Okay. So, valence band is what I told means either completely filled status. Completely filled status means all are in valence band only. Nothing is in conduction band. That you can find out in one of the bodies, say insulator. Or partially filled status means electrons are distributed both in valence and conduction bands. That you can find out in what area, sir? That to be conductors. So, valence band is either completely filled or partially filled. Remember now, this valence band represents the energy range considered by valence electrons, right, which are not free. So, simply say that is the energy range associated with the binded electrons. Associated with what? Binded electrons you can call. Next one of that I go. Who is that one there? That to be called conduction band. What is that conduction band, students? Now I can able to examine the conduction band I go. So, next one I say conduction band. Right. Now I can go for this conduction band. So, as compared to the valence band, what is this conduction band means? It is the energy range associated with what means the conduction electrons. It is the energy range associated with what means conduction electrons. So, range of energy is considered by the conduction electrons. Who are called conduction electrons means those are the electrons which are 100% free from the effect of the nucleus. What are the electrons which are 100% free from the effect of the nucleus? Such electrons are called as the conduction electrons. And what is the energy range associated with that conduction or free electrons? That to be called as a conduction band. So, simply you remember now. So, It is the energy range associated with the binded electrons. It is the energy range associated with what means free electrons, you can call. It is the energy range associated with what? Free electrons. It is the energy range associated with what? Binded electrons, you can call. Confirm my option? Right? So, it is the range of energy considered by what? Conduction electrons, nothing but free electrons. It is the range of energy or probability of energy, right, considered by what I said? Conduction electrons. That is nothing but free electrons, you can call. Right? So now, so simply you remember now, valence band associated with the binded electrons, conduction band represent the energy consideration associated with the free electrons, you can call. And what is the status of this conduction band as compared to valence band means? This conduction band to be either partially filled or completely empty. So this conduction band have the status of what means either partially filled or completely empty, I can call. See this one now? It is either completely empty, and so now it is either completely empty, I call. Where do you get this? Insulators, because all are in a valence band in insulator only, right? It is either completely empty, I call, or partially filled. Confirm my option? So that you may get in conductors. And so now it is either completely empty, I can call, or partially filled. Completely empty you may find out in what area, students? Insulators. Partially filled you may find out in what area? Conductors, you can call. So conduction band is the range of energy considered by free electrons. Valence band is the range of energy considered by binded electrons, you can call. So from this you discuss, once the electron jump from valence to the conduction band, it becomes free. As long as it is the valence band, it will not be free. Once it can jump to the conduction band, it become free, you can call. So to make that electron to become free, how much energy I require? That to be known by a term that to be called energy gap. So energy gap indicate what the energy need by an electron to move from valence to the conduction band to become free, you can call. That to be called as the energy gap. And this energy gap you see here, it is the energy difference between valence and conduction bands. This energy gap is the energy difference between valence and conduction bands, you can call. And it always represents the minimum energy required by an electron to move from valence to the conduction band to become free. Confirm my option? Suppose if the applied energy less than the energy gap, that electron is unable to jump into the conduction band. Got it now? So it is the energy difference between valence and conduction band, I said. It always represents what means the energy required by an electron to jump from valence to the conduction band to become free. Suppose if the applied energy less than energy gap, that electron is unable to jump. So such electron not become free. Got it now? So understand, students? So the energy gap always represent how much is the minimum energy required by an electron to move from valence to the conduction band to become free. Suppose you see this one now. If the gap is more energy required. If the gap is less energy required. So higher the gap, more energy required. More energy required when the electron is tightly bound. Lower the gap, less energy required. When do you require the less energy? When the electron is loosely bound. So indirectly, the size of this energy gap represents the bond days of electron. So the size of this energy gap represents the bond days of electron. Higher the energy gap, more energy required to make electron free. Such electron is tightly bound. Lower the energy gap, less energy required. Such electron is loosely bound. So depending on the size of the energy gap, one can distinguish conductor, insulator and semiconductor. That you discuss next. Suppose if you go for conductors, energy gap is almost zero. If you go for insulators, energy gap is very high. If you go for semiconductors, the energy gap is small. So that's the importance of the energy gap. So energy gap is what I say, energy difference between valence and conduction bands. it always represents the minimum energy required by an electron to move from where to where? Valence to conduction band to become free. Right? So indirectly I told that energy gap represents always the bondage of valence electron. Higher the gap, electron is tightly bound. Lower the gap, electron is loosely bound. Confirm my option? So depending on the size of this energy gap, we can easily distinguish conductor, insulator and semiconductor. Right? So that's the energy gap you can call. This energy gap is expressed by EC minus EV. Okay, so this one now. So what is that energy gap I go? So energy gap I say denoted by EZ. Right? It is the energy difference between what I told, valence and conduction bands. EZ equal to what do you know? EC minus EV I told. It always represent what? Minimum energy required by an electron to become free. Right? Represent the minimum energy, right, required by an electron to become free. Okay, always represent how much is the minimum energy required to make an electron free I told. And so now if the applied energy less than energy gap, that electron is unable to become free. Next, it also represents what means the bondage of electron. Right? Gap is more means tightly bound. Gap is less means loosely bound. Right? Represent the bondage of valence electron. Okay. Represent the bondage of valence electron you can call. So that's the impulse of the energy gap you say. And remember now, this energy gap should be expressed in terms of the unit is what means electron volt. Original energy unit joules you can call. So commonly here to be expressed in terms of the thing is not but called electron volt you can call. Say so now. EZ can be expressed in what I told? Electron volt. EV you can call. So now, what is that EV means? 1 EV equal to 1.6 into 10 power minus 19 joules. So now the students, okay. So energy gap is the energy difference between valence and conduction bands. Already know valence band, you know conduction band, right? So it always indicate the energy required by an electron to become free, right? So if the applied energy less than energy gap, that electron do not become free can call. Confirm my option. So indirectly it indicate the bondage of valence electron. Gap is more means more energy required. Such electron, whenever it require more energy means it is a tightly bounded electron, right? Suppose if the gap is less means less energy required. Such electron require less energy means it is loosely bound, indicating that the band size of the band gap, size of this energy gap represent the bondage of electron. And so now, so this energy gap to be expressed in terms of the unit is what's electron volt. Simple example you see now. Small example I show to you. See for now, this is the water canal. This is one more canal you can call. Two water canals I taken. Here X person is there. Here Y person is there. So they want to jump to the other side of the canal. They want to jump to the other side of the canal. So the width of the canal here is less, right? Small width is there. So this X person can able to jump to the other side very easily and applying less energy to him. Not much high energy required. So on applying less energy, this X person can easy to jump to the other side of the canal. Come back to the Y. So here the width of the canal is long. So it is a wider one. So what is the energy I given to X? If I apply the same energy to Y, he may fall into the canal. He don't go to the other side. So as compared to X, here the width of the canal is wider, you can call. So the energy required for Y must be more as compared to X. Why you require more energy means the width of the canal is wider, sir, such that whatever energy I given to X is not be suitable for him, so that he must give up more energy as compared to X. Why do you need more energy? Means depending on the width of the canal. So the energy needed by Y should be more as compared to X. By that only you can able to jump to the other side as a free person. Same one. Here also the energy gap say that how much energy needed by an electron to jump from valence to the conduction band. Gap less means less energy required. Gap more means more energy required. So now based on this energy gap, I can easily distinguish what is a conductor, what's an insulator, and what's semiconductor. And so now the students, so you discussed what is the atomic structure you learn. Based on that you discussed valence electrons, all that. After that I come back to discuss energy band diagram. So because of electrons not have the same energy, they have random energy, so you know. Based on that you discuss energy band diagram that represent the range of energies considered by the electrons I told in a given atom. So there are 3 partitions in the energy band diagram. You discuss valence band, conduction band, and energy gap. So with this idea you can enter what is a conductor, what's an insulator, and what's semiconductor. Okay, and so now after this